Hey, good morning, everybody. Hope everybody's doing well. We got snow, which was predicted, but I didn't expect it. I think it's in the camera there. Save that for posterity. Snowfall. All right, how is everyone today? Good morning in Chile. Yeah, it's still cold out there. So, Clark sent an alert saying classes before 8 were canceled, and I'm surprised that they didn't say anything about whether remote classes or online classes would be canceled or not. So if Clark says classes are canceled, classes are canceled. But I decided I was going to come here. I was going to lecture anyway. If students can make it, that's great. Come in, you can participate. If not, you can watch the recording later. But since we meet only 2 days a week, we only have 20 meetings for the entire quarter. If we miss today, that's 5% of our material. We can't really afford that. So I wanted to at least come here and do a lecture and talk about the things that I thought we needed to talk about. But I appreciate the people who can be here. I know some people, public schools are closed, so that changes schedules for a lot of people. But glad you're here. And if you have to leave or something, that's totally cool. But let's just go ahead and continue. Yeah, I didn't know it was snowing. I saw the alert that classes were delayed, and about an hour later I looked out the window and was like, whoa. All right, so I'm hoping to talk about homework questions, Lab 1 discussion, Lab 2 overview, go over the remaining things, 2's complement, decimal representation, fractions in binary that you need for homework 1, along with analog to digital conversion, and then I want to go ahead and talk about some new materials. So, any questions anyone wants to start with up front? And I haven't heard any audio from anyone, so it's possible my audio is not working, but if you try to use your mic and I don't respond, send me a chat message. But any questions? Yeah, definitely. So let's talk about protoboards. Hey. So here's a typical protoboard or breadboard, as they're sometimes called. And the basic setup is, if you were to peel away the backing, I don't think I can do that without totally destroying it, but there's all these holes in the top, and some of these holes are connected to each other. And so in Tinkercad or in a lab, if you have a multimeter which can measure resistance, right, what do we know? We know that if you have a straight wire, the resistance between the two ends is 0, right? In other words, a wire does not impede the flow of current. If you have a resistor, which is, typically a little piece of carbon with wires going to the end, it's harder for current to pass through. And if you have two things that are not connected, then it's very hard for current to pass, from one point to another through the air. And so the resistance will be close to infinity. Is it actually infinity, or are there cases under which current could flow from one point to another without a piece of wire connecting them? What do you think? It could if there was moisture in the air. It's possible for current to flow from one point to another even with nothing but air in between. This is what happens with lightning, right? Lightning is a current flow between typically the ground and a cloud, and there's no metal conductor there. If there's a big piece of copper rod going up that will conduct. But even with just air, you can get current flow. But you need a lot of current to make that happen. Same thing with static electricity. If you get close to a doorknob on a really dry day, you may get a little shock even before you physically touch the doorknob. The voltage is high enough that it can push the current through a little tiny air gap. Right? If you have a car with spark plugs, same thing happens there. The spark plug is something that creates, a little spark. What's a spark? It's a jump of current from one point to another through typically an air gap. And when you work on your engine and you have those little spark plug gap gauges, what you're doing is adjusting how far apart those two pieces of metal are so that they're just the right distance, that you have to get up to just the right conditions before that spark jumps. And those conditions are optimal for the biggest explosion in the cylinder, etc. So this does happen. But anyway, protoboards, some of these points are connected to each other. For example, all 5 of these holes you'll find are connected together, and all 5 of these holes are connected together, but there's no connection horizontally from here to say there. There's no connection from here to any of the holes in these rows. But everything in right here is connected together. And so you have on this board, it's labeled out to, I think 64 columns of holes on the bottom, 64 on top, all connected. And then we have 4 special rows, one on the very top. All of these under the red line are connected, all of these under the blue line are connected, and the same with these. So what you can do is, if you want to connect 2 pieces of wire together, you can simply plug them into any set of holes that are connected to each other, and bingo, this end of the wire and this end of the wire are now connected because they're joined through that column. And so let me grab some parts. And so these are kind of like integrated circuits. They're not actually, but same idea. So these pins on this board, this pin right here is plugged into a hole right back here, and so it's connected to every hole in this column. And so by putting a wire in here, this yellow wire is now connected to this pin on this board, and the yellow wire runs over to this point right here. And this switch has 2 little metal conductors, one right there, one right there. Well, this conductor here is connected in the same column as the yellow wire, so I've just made a connection between this part of the switch and this pin on this little circuit board. And if I used integrated circuits and plugged those in, straddling the middle here, same thing, I can get to their pins by just plugging into those columns. And then if you have things like resistors, you can plug those in, or LEDs, you can plug those in and make connections to them. And so this is a general way that you can build a circuit without having to solder and desolder wires. It lets you just make connections directly from one point to another. So when we do this class in person, or when you do 270 or ECS 120, you get these in your parts box, and you get a big pile of parts, and you actually build your circuits by placing them in the holes and connecting them with wires. In an online version, we do this with Tinkercad, and it simulates the proto board, but it's the same basic design process. So the lab itself, question 2 on the protoboard connectivity just wanted you to do some analysis in Tinkercad, see what's connected to what, and then draw a line. So you end up with a bunch of vertical lines, 30 up here, 30 down here, and then 4 horizontal lines going across like that. All right, other questions? I'm switching back camera views, hold on. Yeah, let's talk about system diagrams. Oh, let's see. All right, one sec. One sec. All right. So yeah, let's just go through lab 1 in detail, and then we can talk about homework. So lab 1's got graded if they were turned in by yesterday. And really good work on the lab. So normally the kind of lab reports I'm seeing, normally we're into like week 5 or 6 before people are doing this quality of work. So I'm seeing like really good good reports, including the pieces that are supposed to be included, documenting things well, and so on and so forth. So I'm super pleased with the lab reports that people turned in. It's definitely a pleasant surprise. So let me talk about specific issues, and there weren't that many. So the main mantra of labs are, you know, they should be self-contained reports that tell you everything you need to know about what somebody did. And most people got that. They nailed it. And, you know, usually in 270, I'm still fighting to get people to do that. So this was fantastic. So yeah, your lab report should not just be, you know, experiment 1 and then a bunch of numbers or something. It should be, you know, complete sentences, paragraphs, stories explaining, you know, what happened, what you did, why you did it, how you did it, what you observed, what you conclude, and so on and so forth. And I saw that in most cases, so excellent job with that. So specific things that may have cost points. So I would like a separate cover in the beginning of the lab report. I want the first page to be basically your name, ENGR250, the date, and something that says, you know, lab 2 or whatever the lab number is. If you want to list your instructor, you can do that. You can say instructor : if you want to list lab partners, if you have them, you can put that on there. But this is, you know, this is the cover sheet. This is the thing that if somebody physically picked up a copy of your report, they could look at this and they could see, you know, with no visual clutter exactly what this is. Oh, this is so-and-so's lab 1 report for ENGR250 in spring 2022. This was done in April. And that's all that goes on the cover page, right? Put a break in there and then continue with your introduction on the second page. So I didn't take off points for that, but I put a comment in there saying, you know, make sure you put in a separate cover sheet. And then again, I want an introduction to the lab itself. And so, you know, introduction, and could be one sentence, right? In this lab, we worked with Tinkercad to learn about the basic components, study their parameters, study protoboard connectivity, etc., etc. right? All right, let's see. So experiment 1 asked for you to describe the parameters that you can change and its associated range. So, you know, resistors, you can set the name, you can set the resistance. What's the range of resistance? Well, I don't know, but it gave options for, I think, from pico ohms up to giga ohms. So you could mention that, and it appears you can put in, you know, pretty much any number in the box that you want. So presumably, you know, any range, any resistance that you want. LEDs, you can set the name and you can set the color. So what are the possible colors that you could select? So I wanted to see that information for each of these devices. What are the things that you can change or specify about this? Those are the parameters. And what are the possible values? So you needed both of those things. Experiment 2, protoboard connectivity. Again, you can measure this using the multimeter. And I guess let's go ahead and do that. So let's go ahead and put a protoboard in here. And let's get a multimeter. And so if I run some wires, like run a wire from here to here, and right now this meter is set for volts. That's what the little V means. If I change this to resistance, then you can see the little R here is marked. And so if I go ahead and I run this circuit, run this circuit. So it's showing me, you know, it counted up and it's showing me mega ohms, right? Which tells me basically infinite resistance between this point in column 25 and this point in column 26. I don't know if I can monkey with these while the circuit is running, but let's try. I don't think so. Alright, so let's stop the simulation. Let's grab this end and put it in column 25 and then run this again, and now you see a resistance of 0 ohms. So that tells me this point and this point are connected together. And you know, Tinkercad, when you hover over a square, it highlights a bunch of points, and you pretty quickly start to think, hey, maybe all of these are connected. Hey, maybe all of these are connected. So you do a few experiments, right? You're not going to try every possible combination of two circles to see what's connected, but you know, you come up with a theory. Hey, I think all of the things in these columns are connected together, but I don't know about, you know, if I cross this middle barrier. What if I take this and I move it down here? So it's in the same column but on the other side. Well, that's disconnected, infinite resistance. So everything here is connected, everything here is connected, but there's no connection between this upper column and this lower column, and so on. So that was experiment 2. And so, you know, if all you had was a picture of this with some lines, I let you get away with that. But you know, you did something to decide what the connectivity was, and you should describe what that is, because again, the idea is somebody else will take your lab report, they'll try to reproduce your steps, right, and come up with the same result you did. And if they do what you described and they say, hey, you know, columns 17 and 18 seem to be connected, well, now you've got something interesting going on, right? Maybe not all protoboards are the same. Maybe someone's is defective. Maybe you missed a connection, right? So it's about trying to validate results. All right, experiment 3. So you were connecting a function generator to an oscilloscope, And let's just play with this. So there's an oscilloscope. I'm going to do this without a proto board. So this terminal on the left is labeled negative, and negative is ground, which is also the black terminal. Positive is sometimes called hot and is usually the red terminal. And so I'm going to connect positive over to red, and then I'm going to connect ground, negative to negative. So there's a hookup of our oscilloscope. So what is an oscilloscope? What's the deal here? Suppose you build a circuit, like in engineering computer science 120, and you have 2 points and you want to know what the voltage is. So you take a multimeter, right? And you have 2 leads coming off a multimeter. You put one lead at one point, the other at the other point, and you set the knob to voltage, and it tells you this is, 3.6 volts. And you change a switch in your circuit, or you move a wire, and now it tells you it's -1 volt, right? And so if your voltage is not changing, you can use this piece of equipment to figure out what voltage something is. But there's a challenge if you have something like this, where you have time and voltage, and your voltage is changing. If you use a multimeter to measure this, every time the multimeter takes a sample, you're going to see a different number, and the display is going to change, maybe 5 or 6 times a second, and it doesn't show you that this voltage is changing in this nice smooth shape of a sine wave, or a square wave, or a sawtooth wave. So the oscilloscope is like an advanced version of a multimeter. It's a way to measure voltage and see those measurements graphically, because it's easier to see what's going on with a picture than to just see a bunch of numbers and try to figure out what those numbers represent. And an old school oscilloscope works like this. It's got a display, it's got a cathode ray tube. That's what TVs used to have, right? So it's a phosphorescent covered piece of glass and something in the back that shoots a beam of electrons. And so side view, here's an electron generator. And you heat up a piece of metal, it'll spit off electrons. And so you've got a bunch of electrons flying away from this thing. And you have a magnetic field, which you can control by running current through a coil, right? We talked about this before. If you run current through a coil of wire, you get a magnet. We talk about it in 101 at least. So you have this beam of electrons going in between these 2 metal plates, but if you magnetize these plates, this beam will start to change direction, and it might go up or it might go down. And then over here you have this piece of glass coated with some kind of compound that lights up when electrons hit it. So it's a phosphorescent compound. And so all things being equal, if you don't put a magnetic field on these plates, you get a little spot right here. But if you apply a voltage up here, which creates a magnetic field of a certain type, this beam will start to deflect, and the place where the electrons hit the plate will increase. And so you can control the appearance of the spot to be up or down, or by changing the polarity you can come down below the middle point. And so if you look at the front of this, you would see a dot that moves up or moves down. Alright, well now you put another pair of plates, one up here and one underneath the desk, and same thing, you can move this beam left or right. So with two voltages, you can control which point of phosphorescent material gets illuminated. And you hit it with electrons, it lights up. When you stop hitting it with electrons, it fades, but it fades pretty quickly. Fraction of a second. So how do you make a picture on something like this? For example, for a TV set, you change your voltages to move from the upper left corner all the way across to the upper right, and then come back and move but slightly lower, and come back and move but slightly lower, and so on, and you do what's called a raster sweep. And you keep doing this until you've come down to the bottom, and then you come back up here and you do it again. So by changing these voltages on this horizontal deflection and this vertical deflection, you would light up the entire display. But now you take your electron generator and you turn it on and off. And if you want a spot right here, you leave this generator off until the deflection plates are pointing the beam at this point. Now you turn it on, and that spot lights up. And if you want this spot to be lit up, you wait till the beam gets here and you turn it on. And so by turning the beam on and off, you can get a pattern. And same thing, when you get to the end of one raster line, you want to come back to the next line, you turn the beam off as you sweep back. So that's called a flyback. And you do that all the way to the bottom. And when you get down here to the last point, you want to go back up to the upper left, you turn the beam off and you change your place to come back up here, and you start the whole thing again. So that's a general video display. That's how TVs actually work. That's the behavior that's emulated with LCD panels today. But to make an oscilloscope, we do exactly the same thing, except that we basically have one plate just continually moving the beam from left to right and then coming back. So we're not doing this sweep. We just go from left to right, come back, go from left to right, come back. But as we're moving from left to right, what controls the vertical deflection? The signal that you're sending into your oscilloscope. So this signal coming in here, this positive-negative pair, is being used to drive a vertical displacement of this electron beam. So the beam is sweeping from left to right, but if there's a positive voltage, the beam is also being deflected up here. And so we're seeing a line drawn up here, and if that voltage begins to drop, now the deflection becomes less and the beam starts to come down, and so we see our line coming down. And then at this point, if the deflection starts to go positive again, the beam will start to come up. And if you set this up just right, you get a nice little picture of a waveform. So if we set this to a sine wave, and this is 1 kilohertz, 5 volts, 2.5 offset, and we run that, then we'll get something like a sine wave. So, but this doesn't look like a sine wave, right? So what do we have to do? We have to control how fast we sweep from one side to the other, and we have to control for a certain input voltage how much do we deflect the beam up or down. And so if we have a very small signal coming in, so let's do a cleaner picture of the scope. We're moving from left to right, and we're sampling an input signal, and we're deflecting up and down. Well, if your input voltage is really, 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 really small, then instead of a straight line, you might get something like this. Right? Not very interesting. So if your signal is very small, what we want to do is say, hey, you know, if you get a 1 millivolt input, let's deflect the signal up to here. And if you get negative 1 millivolt, let's bring the signal down to here. Oh, thank you. And so now this little tiny scribble that you're coming in looks like this really interesting waveform that you can easily see. The other thing is, if your signal is changing very, very slowly, and the time from here to here is a nanosecond, well, you're just going to see this thing coming across for a nanosecond, and your waveform is slowly increasing. You're just going to see sort of a line that slowly rises up and slowly rises down. But if you slowed down how long it took to sweep from one side to the other, you might start to come across like this. And let's say after a millisecond your signal is starting to rise, right? Well, if it takes a millisecond to get from here to here, then you'll see your waveform start to come up and slowly come down, and so on and so forth. And on a physical scope, you need to control something so that, you know, if my waveform started at 0 and it ended up here, it doesn't come back and start drawing at this point, because then you're going to get a big mess. So there's something called a trigger, and you can say, okay, I want you to start only when I'm crossing this point from negative to positive. So now your waveform is continuing like this, but it's only when it gets to this point that the electron beam comes back here, and now you get another replication of that image. So these knob settings that you're using in Tinkercad are controlling those parameters. So right now it's saying 1 second, there's a 1.00s on the bottom. That means the time it takes the waveform to go from this end of the display to that end is 1 second. And so since there's 10 marks here, it takes 1/10 of a second or 100 milliseconds to go from one of these lines to the next. And over here on the right is the amplitude, 20 volts. That's 20 volts from the bottom to the top, which means each of these lines is 2 volts. Now our waveform just changed, right? It just jumped there. Well, that's because, you know, we're taking a second to go from here to here, but this waveform is changing 1,000 times a second. So let's change these parameters. Let's say that the time per division is 1 millisecond. And I don't know if it'll let us do this while it's running or not. There we go. So now it's 1 millisecond from one of these vertical lines to the next. Well, if we look at our waveform, it goes from, say, you know, the middle point here, right, 1.5 of these gradients, from there till it goes up and down and comes back again is this point right here. Well, the distance from there to there is 1 gradation mark. Since it's 10 milliseconds for 10 marks, each of these is 1 millisecond. Right? And that's what we set, time per division. So a division is, you know, from one vertical line to the next. So our waveform is going up and down in 1 millisecond. If you convert that to frequency, that's 1,000 times it goes up and down per second. That's what this knob is setting right here. 1 kilohertz, that's 1,000 cycles per second. If I make this 100 kilohertz, well, our waveform looks kind of like a blob. It's going up and down, you know, 100 times in a millisecond. And so since the distance from here to here is a millisecond, there's 100 up and down cycles in here. We can't see those. But if we change this to, say, you know, 1 microsecond, we'll see something a little more usable. And when you try to do this live, right, it's trying to update the display while responding to your clicks and so on. So sometimes it's better to just go ahead and stop this. So there's 1 microsecond. And so down here, this little 10 microsecond is telling me it's 10 microseconds from one end of the display to another. Well, we're at about 100 kilohertz, which means about 10 microseconds for one cycle. And you can see that's what we're looking at. We're looking at one cycle. It starts at this level, goes down, goes up, comes back down to this level. There's one repetition of your waveform. So if you're doing an experiment and you're using an oscilloscope to take measurements and you're trying to document those, what do you want to put in your lab report? You can put a picture of your oscilloscope in, and you know, if it's got these units marked, that probably tells the reader everything they need to know. But you could also, you know, add some extra information on here. For example, you could put, you know, a mark here and indicate that that's exactly 1 microsecond in time. And you could put a mark from here to here and say that's 2 volts. Or, you know, since my waveform seems to go from this peak up here down to there, you could figure out what that distance is. And in this case, that's 2, 4, and a half of 2 is 5. And you could put a mark here and a mark down here and then something to indicate that's 5 volts. And now somebody can look at this waveform and say, oh, it's going from 0 to 5 volts. And, you know, it's waggling this quickly. So this is a lab that if you did this in the actual lab with physical equipment, there's a whole lot more you'd be doing, right? It's a really useful but fairly complex piece of equipment, an oscilloscope. But it's the only thing you can really use when you've got signals that are changing quickly over time. If you have a signal that's changing 1,000,000 times a second, you can't really figure that out by hooking up an LED or hooking up a multimeter. You need an oscilloscope, and so that's a really useful piece of equipment. And we put these experiments in this lab to introduce people to this, but most students don't end up with a comfort level of oscilloscopes to let them use them. And so they get to other labs like in 270 and they're struggling to figure out what's going on, and they don't have, you know, the tools they need to use this piece of equipment. So this is a really important part of the lab. Alright, so so you did 3 experiments and you changed the frequency. The duty cycle was always 50%. You changed the voltage, amplitude, and the bias. And so 5 volt peak to peak, 2.5 bias, that's what we just saw. And it basically goes from 0 volts up to 5 volts. With a bias of 0, normally it's centered around this 0 volt line. But with a bias of 2.5, it goes from -5.5 to 0 up to, minus 2.5 plus 2.5. Changes from 0 to 5. Alright, and then 3 volt peak to peak with no bias, that'll change from -1.5 to +1.5 volts. And then 4 volts peak to peak with a bias of 2, that'll change from 0 to 4 volts. So this middle one will be symmetric around the horizontal axis. Alright, and then experiment 4. So experiment 4 is super critical because this is going to get built on in lab 2, 3, and I think lab 6. So we come back to this one a few more times. So first thing was sketching the intersection. So we specified in class that even though the lab report doesn't say it, your intersection has to be situated like this, and you have to label these west, south, and east, not A, B, C, 1, 2, 3, etc. So west, south, and east, and the idea is you have a sensor for each lane, and you have 2 lights for each lane. So you have a west green or a green west, and a west red, south green, south red, east green, east red. And it's easiest just to call your sensors WSE, so that when you write Boolean equations eventually, you have single letters for those. And rules of Washington State, this is highest priority. On the east, this is lowest. In a real system, you know, you might allow east and west traffic to go at the same time because they're on opposite sides of the road. But this is a simplified intersection. So only one lane gets a green light. All the other lanes get red lights. All right. So, system diagram. System diagram is your 40,000 foot view. So without worrying about how the circuitry is designed, without worrying about truth tables or equations, what's the basic input-output picture of this circuit? And so you have three inputs. These are car sensors. So I'm going to label these as sensors. I'm going to say 1 equals car, 0 equals no car. And that's important. There's some sensors that if a car is present, it will output a 0. And if there's no car, it'll output a 1. So I need to know that for this circuit that I'm designing, I'm saying, hey, put a 1 into here if there's a car on the west. Put a 1 into here if there's a car on the south. Put a 0 into here if there's no car on the east. And then there's 6 outputs because we have 6 lights. So we have west green, west red, south green, south red, east green, east red. And our outputs are Boolean also, so we have a 1 and a 0, and so 1 means that light is on, 0 means the light is off. Again, you could do this differently. You could use negative logic to say when this is a 0, the light should be on. When it's a 1, it should be off. But you have to specify. So somebody knows how should they hook their lights up to these outputs to make them do the right thing. Alright, well once you know what your system diagram looks like, you can make your truth table. And so here's what your truth table should look like. So here's the inputs, and then let's do east green, south green, west green, east red, south red, west red. It doesn't matter what order you do these in. I'm going to do them in this order because it will make it a little easier to write. Alright, I strongly recommend numbering your truth table in this order. Had a few truth tables with missing rows in them, and that's a problem because if you don't know what should happen in this combination, you can't design the circuit. So make sure you have, 8 rows if you have 3 inputs. And so how do we fill in this table? Well, I'm going to look at the greens first, and I know that east is the highest priority. So anytime there's a car to the east, I want my east green light to be a 1. And only one light can be green at a time, so south and west have to be 0 at that point. South is the second highest priority, so if there's nothing to the east but there is a car on the south, south should be green. So east is 0, south is 1, south should be green. And then in that case, east and west will be red, so the green lights are off. And then lowest priority is west. West gets to go if there's a car to the west and there's nothing to the east or the south. So car to the west, nothing on the east or the south, that's when east gets to go. And then what will you do in this situation? You could turn all your lights red, you could pick one light to go green. And so it'll turn out to be a little simpler if you make this a 1 0 0. But you could make it 0 0 0, or you could just say, hey, I like south, let's make south green, or whatever. Alright, and then the red lights are just the opposite of the green lights, so this should be 0 1 1, 0 1 1, 0 1 1, 0 1 1, 1 0 1, 1 0 1, 0 1 1, and depending on how you want to set that up. So there's the truth table that describes how the lights should change for this intersection. So if you only had 3 outputs, you lost points for that because you've got 6 outputs in your system diagram. And the outputs are not something like red, green, right? The outputs are binary, ones or zeros. And you know, in some versions of this lab, we let people say, okay, the output 1 means green, 0 means red, for example, but we said explicitly don't do that because that will only work for the first few versions of this. So I wanted 6 outputs, each of them a 1 or a 0, to say whether the light's on or off. And so most people got that, which is great. But if you lost points on that, it's probably because you only had 3 outputs instead of 6, or your truth table only had 3 outputs instead of 6. Let's see, truth table, at most 1 light should be green, right? So if you just look at the green lights, there should be at most a single 1 in any of these cases. And if I had a 1 and a 1 here, you've got a problem, right? We've got 2 lanes that are going at the same time. That's not allowed. You could have all zeros here if you wanted. And that's a case where, hey, there's no cars, all the lights are red. So that's legit. What else on experiment 4? I think that was the main thing. So having the intersection, the system diagram, 3 in, 6 out, explanation of what the 1s and 0s mean for those, and then the truth table, 3 inputs, 6 outputs, and at most 1 lane is green at a time. And I think those are all the situations that we ran into. All right, new experiment. So, again, at the end of the lab, you're required to come up with a new experiment on your own, right? And this should be related to the themes of the lab, but it should not be a variation on an experiment you've done. So, you know, redesign your circuit to use blue lights and yellow lights instead of red and green. Well, that's a variation of what we already did, right? So that wouldn't count. And it should be an experiment as opposed to a homework problem. So I got some new experiments that were like, you know, simplify this truth table, or combine these resistors, or draw a system diagram for such and such. It should be an experiment, something that involves using equipment and coming up with a circuit, and you know, or that's leading to that. So try to make it something fairly involved, and you know, it's the last experiment. It should be, in some ways, the most challenging. And so we'll talk about that for lab 2 in more detail, but going forward, you're going to want to come up with a new experiment. I'm going to say going forward, your new experiment cannot be anything related to a traffic light. All right? So we're just going to take that off the table. Because, you know, most of these labs are going to have a traffic light component. I don't want new experiments that are about traffic lights. Try to come up with something that uses the same ideas that we're developing in a lab, but applies them to something different. And then after you design the new experiment, and again, it needs enough detail so somebody would know exactly what to do, you're going to need to actually do that experiment and write it up. So if it says, you know, build a circuit to travel backwards in time, I'm going to expect you to actually build that circuit, come up with some experiments, perform those experiments, make observations, document those observations, and so on. All right, so this makes it more challenging to come up with a good experiment. But I really want you to spend time thinking about, what are we doing in this lab? What are the themes? What are the things that we're learning? What are we developing, exploring? And exercise that by coming up with another experiment of your own design to continue that area of development. All right, the only other thing I'm going to say in here is don't copy text, figures, things like that, unless you cite your sources. So if you're writing up experiment 4 and in your lab report you say a three-way intersection needs a traffic control system, each direction has only one lane, right? Those are not your words. Those are words taken from somebody else. You need to indicate that those are not your words, right? So you could put this in quotation marks and then put a footnote, and then at the end of your lab report or down here you could put a footnote and say taken from, Engineering 250 Lab 1 version such and such, and so on. But a better option is put things in your own words. All right, so paraphrase what the goal of experiment 4 is. But if you want to, use words verbatim, you've got to cite where they came from. Otherwise, technically, that's considered plagiarism. And this will happen more with figures, right? So if there's a circuit diagram in a lab, and you want to include that in your lab report, you can do that. You can cut it out of the PDF and paste it into your lab report. That's fine, but put a note at the bottom saying, figure taken from Engineering 250 Lab 2, blah, 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 right? So make sure that somebody can't claim that you plagiarized. So, writing, put it in your own words. Pictures, if you don't want to redraw them, just put a citation and say where you got it from. So question in chat, what if we choose to do a difficult circuit for the new experiment or we're not able to make it work? That's okay. On these experiments that we give you in the labs, it's possible that, for some of the later ones especially, you may not be able to get it to work. And that's all right? You should still write it up, describe the procedure, run the experiments, make your observations, document all of that. And if you're not getting the result that you expected, just document that. Explain it, discuss it. If you have some theories what might be going on, you can talk about that. If you can imagine, if I had unlimited time, how would I dig into this? You can talk about that. And, if you get the expected result, that's great. But sometimes you don't. And, in a physical lab, sometimes you find out your proto board is buggy, right? Maybe the connections aren't all making contact anymore because somebody had a chip on there, they hooked it up backwards, they melted something, and now it's not making contact, right? So the goal of doing science is to confirm or refute other people's results. And so if you're not getting the result that you expect, that's totally legit. Just go ahead and document that. Now, if your circuit doesn't work the first time, don't just, take the easy out and say, oh, this didn't work, I guess science is wrong, right? You should be able to get, the expected results. So you have to do enough work to get there. But if you can't, right, especially if it's a new experiment you come up with where maybe it doesn't work the way that you think it does, right, just go ahead and document that. And in some cases you could still get full credit. Especially if you're making a time machine and you're introducing paradoxes and stuff, right? So. All right, and then everybody had conclusions, lessons learned, so that was good. Keep that up. And so yeah, again, this is like the highest across the board scores I've ever seen for Lab 1 of 250. So keep up the good habits, the good work, and I posted feedback again. Even if you didn't lose points, there may be feedback in there that could cost you points in the future. So make sure you read the comments if I posted any on your report. And I think everyone's in good shape for Lab 2. All right, any other questions? All right, let's go ahead and talk about Lab 2, and then we'll maybe take a break, and then we'll talk about the homework and continue building from there. But let's keep going with Lab since we're here. All right, so Lab 2, we're going to start designing and building circuits on the protoboard and doing some experiments with them. So, overall goal, apply understanding of logic gate, system diagram, truth table schematics, and logic circuit design. So this will also include a traffic light experiment at the end, and we're going to move from the truth table to the next level of design. But first we're going to play around with some LEDs. So LEDs are these little, usually red light bulbs, right? That that can turn on or off. Let me see if I have an LED here. Sadness, no LEDs. But they look like this. They have longer leads, but it's this little, you know, sort of oval ellipsoid shaped thing. It's circular with a little flat piece on one spot and two leads coming off. So LEDs are polarized. There's a plus and a minus, and the polarity matters. So, you know, plain old light bulb, you can hook it up, plus, minus, minus, plus, it lights up. LEDs, there's one side called a cathode, which has to be on the negative side, and an anode, which has to be on the positive side. So your current flows in this direction. This is the symbol for it, and the triangle shows you which direction current's flowing in. You need this vertical bar to make it an LED instead of what's called a buffer. And if you run current through here, the LED will light up. And a physical LED, you need to do something to figure out which lead is which. So the positive lead has this little bend in it, the negative lead is on the flat piece, and if you hold an LED up to the light, the negative lead connects to a big old piece of metal, the positive connects to a small piece. So there's different ways. But on Tinkercad, right, they're labeled positive, negative, or anode, cathode. There's also LEDs that are much smaller. So each of these little rectangles is actually an LED, and it's just got a connection at one end or the other, and these just light up. It's pretty hard to see that they're lit, but you can see them when they change. And LEDs come in different colors, just like in Tinkercad. So there's red and yellow and green and blue and white, and they can come in ultraviolet, and they come in infrared, and so all kinds of things. So the other thing to know about LEDs is they can only handle a certain amount of current. So the rating of this, the current flowing from positive and negative, should be less than 30 milliamps at 2.5 volts. You can put 5 volts through here. You typically want to put through about 5 milliamps. If you go above 30, the LED will probably pop, and it makes a noise, and it smells bad, and it doesn't light up anymore. So there's a limit to how much current you can put through, and so whenever you hook up an LED in a circuit, you always put it in series with a resistor. And typically the voltage drop across an LED is pretty close to 0. So if you want to do some basic circuit analysis, so here's ground, and let's suppose we put 5 volts into this end. Well, since the voltage drop across here is typically 0, we can think of this as being, you know, approximately 0 volts. Well, if you have a 1 kilo ohm resistor and you have some current flowing through it, what does Ohm's law tell us? It tells us the voltage is equal to the current times the resistance. Well, the voltage from here to here is about 5 volts. That's equal to the current times the resistance, which is 1,000. And so your current is 5 over 1,000, which is 0.005 amps, which is 5 milliamps. And in a series circuit, current is the same everywhere along the circuit. So that means you also have the same current I flowing through the LED. And so with this configuration, you get 5 milliamps flowing through your LED in the positive direction, right? From the anode to the cathode, positive to negative. This will light up the LED. If I cut this down to 100 ohms, my current will be 5 over 100. That'll be 50 milliamps. That's probably going to burn out the LED. So typically we use 1K in series with an LED to display a signal visually. And basically if you have 5 volts, which is logic 1, your LED turns on. And if you have close to 0 volts, which is logic 0, your LED turns off. Alright, that's everything you need to know about LEDs. So we do some experiments. We're going to build 3 circuits. So you're actually going to build these in Tinkercad. So you're going to put 5 volts over here, run it through a 1K ohm resistor, run it through an LED, take the other end of the LED, hook it to ground. And then run your simulation, see what happens. Does this light up? Does it not light up? Does it explode? When LEDs explode in Tinkercad, you get this little explosion symbol around it. It's pretty fun. Alright, configuration 2. This is an inverter. It's a 74 LS04. So take an inverter, hook it up to your protoboard, make sure you connect pin 7 to ground, 14 to power, and then the L, which is low, is 0 volts, which is the same as ground. So take the input of one of your inverters, connect it to ground, take the output of the inverter, feed that into your LED, take the other end of the LED through a 1K to ground, run your circuit, observe what happens. And then configuration 3, H means high, which is 5 volts, not 54 volts, 5 volts. So hook this up to 5 volts, go through an inverter, take the output of the inverter, hook it to the negative end of an LED, take the positive end of the LED, run that through a resistor, hook this end to VCC, which is 5 volts. Run your simulation, record what happens. So these are all different ways of hooking up LEDs. And then try to explain why what you observed is what happened. So if the LED was off in this configuration, try to explain why. If it was on, try to explain why. If it exploded in this configuration, explain why. And for all of these, all you need to know is that if you have, at least 2.5 volts going from this end to that end, with something, between, say, 5 and 30 milliamps, the LED should turn on. And if you don't have that situation, the LED should be off. And if you put in more than, say, 30 or 40 milliamps, the LED will probably explode. It doesn't actually explode, it just burns out. Alright, experiment 2, we're playing with switches. So LEDs are used for outputs, switches are used for inputs. So let me talk about switches first, independent of this experiment. And this is one of these things that you'll use throughout this course, and you'll use it in 270, and you'll use it in other situations. So this is fairly important. Let's say you have some circuit. Maybe it's a traffic light controller. Maybe it's a combination lock. But you have some input, and you want to put in either 5 volts or 0 volts. And if you're designing your circuit and you want to test it, right? To test it, you want to change what your inputs are. So how do you do this? Well, one way would be to take a wire from here and either connect it to the 0 volt part of your power supply or the 5 volt part. And so you can move your wires around. And that's fine for testing, but it's not really good for high quality production use. So a second option is to have a switch. And you could have a switch which goes to either 0 volts or 5 volts. And this could feed your input to your circuit. And so if you flip your switch in one direction, it connects 0 volts to this point. If you flip it in the other, it connects 5 volts to that point. And so that's another way to control your input through a switch. But most switches that we encounter are not this complex. Most switches that we encounter look like this. If you press the switch or put it in one position, you connect this point to this. If you put the switch in the other position, you disconnect this from this. And so little slide switches like these, right? You can slide these things down or you can slide them up. And they're open or closed. So this would be called open. And this would be called closed. And these simple switches, you don't have two places you can connect this output to. You either connect this side to this side, or you disconnect this side from this side. And if you have something like a logic gate, well, we know if I connect this to 5 volts, the output will be 0, because it's an inverter. And if I connect this to 0 volts or ground, the output will be 5 volts. But if I don't connect this to anything, what do we think the output's going to be? If I just leave this floating. So nothing is a good answer, but voltages can't be nothing. There's always some voltage. If we hook a meter up here, it will give us some number. And pretty common intuition says, you know, if we don't connect this to anything, it's a 0. But it's really not. It can be a few different things. It could be a 0. In certain kinds of chips, if this is a 74LSO4, disconnected inputs actually end up being logic level 1 for various reasons. But the more common situation is this is unknown. And depending on what's going on in the universe, this could at any given point be a logic 1 or a logic 0. It might be a logic 0 and then somebody walks by with their iPhone and they get a phone call at that moment, and all of a sudden this is treated like a logic 1. And your output goes from a 1 down to a 0. So open inputs are sketchy, right? Having an input to a gate that's not connected to anything, usually a really bad idea. We want this either connected to 5 volts or 0 volts. So how do we wire up a switch? So this is one of these things that by the end of 270, I'm still struggling usually to get people to wire switches correctly. I have a feeling this class is going to nail it. So let's look at how we can do this. We want to feed either 0 volts or 5 volts. So here's what we're going to do. We're going to take a 1K resistor. We're going to tie our input to 5 volts through a 1K resistor. And then we're going to take our simple switch and make it look like this. So this is sometimes called a pull-up resistor. And what the pull-up resistor is doing is saying, hey, if my switch is open, if it's not connected, this input is not really just sort of like floating in the air. It's actually being pulled up to 5 volts. So if my switch is open, my input is at 5 volts, which is a logic level 1. But if my switch is closed, if I take this switch and I push it down like this, what is my input voltage going to be? This is an Engineering 120 flashback. If my point right here is connected to ground, what's my voltage at this point in? So let me redraw this a little differently. So this is what the circuit looks like right now. So I have 5 volts up here, and then I have a resistor, and then I have my input connected directly to ground. And so this will actually end up being 0 volts. And the reason for that is, yeah, my input's connected to 5 volts, but it's connected through a resistor. And what I'll see is that across this resistor, I get a 5 volt drop. But since this is connected just through a wire, right, through a piece of metal directly to ground, this has got to be 0 volts down here. So in this case, the thing I'm feeding to my circuits is 0 volts, which will be a logic 0. Alright, we won't do the KVL, KCL analysis, but think about that. And you can build this circuit on Tinkercad and experiment with it, right? And see what exactly this does. But so this gives us a way to generate either 5 volts or 0 volts with this simple switch circuit. And if the switch is up or disconnected or open, this will be 5 volts. If the switch is down or closed or connected, this will be 0 volts. And so we can generate these two clean logic signals. And this resistor is super critical. If this was just a wire and I closed my switch, I'm going to overload my power supply. Because if this is a wire instead of a resistor, what does this circuit look like? It's 5 volts connected through a wire to ground. Well, how much current do I have? We know that V equals IR, our voltage is 5 volts, our current is unknown, our resistance is 0 volts, and so our current is 5 divided by 0, which is about infinity. So this is called a short circuit, and it's an attempt to draw infinite current from the positive to the negative. Well, our power supplies won't put out infinite current, but they'll overload, and usually a little red light comes on and the safety circuit clicks in inside and it stops putting out any voltage. So we need this resistor here, this pull-up resistor. We need a switch here. And this is the way that you want to wire switches usually for all these labs, in 270. And this end of the switch goes to ground, this goes through a pull-up to 5 volts. There's several other variations of this you can make. Most of them do not work correctly. So this is the one to go to. Alright, so experiment 2 is playing with this. So here's these little slide switches, and here's what they look like. And if you slide this little piece of plastic to the on position, or if you click it in Tinkercad, then this closes and makes contact from one side to the other. So these are little, 8-pin devices, 4 pins here, 4 pins here, and you can connect a pin on the top to the corresponding pin on the bottom by sliding this little piece of plastic to the up or on position. Alright, so you want to build the following circuit. These triangles represent ground. The arrow represents 5 volts. So 5 volts here, 0 volts here, a 1 kilo ohm resistor right there, an inverter, 2 LEDs hooked up in this way, and then another pair of 1K resistors. And things will happen depending on whether the switch is open or closed. So build this circuit, and then have the switch be open and observe what's happening to your LEDs, and then have the switch be closed and observe what's happening to your LEDs, and then make a truth table. And when you make your truth table, here's what you use for ones and zeros. If the switch is closed, meaning it's making contact from one end to the other, that's a logic 0. If it's open, it's a logic 1. Right? That's the behavior that we're getting from this kind of switch. Open is a 1, closed is 0. And then for the LEDs, L1 and L2, if they're turned on, that's a logic 1. If they're off, it's a logic 0. So make yourself a table. Switch, logic 1, or lamp 1, lamp 2. And it should be, 0 and 1, and record what's happening for each of these lights. And then think about this circuit and see if that makes sense. Alright, this experiment is really hard to guess the behavior, and it's really hard to get perfectly right unless you go very, very carefully, methodically, step by step. And I would build this circuit, and then I would make a table that actually said, here's our switch, here's L1 and L2, and instead of using zeros and 1, let's say what happens when the switch is open, what happens when it's closed, and are these lights on or off? In other words, record the observations that you're actually observing, and then go back and try to change them to ones and zeros using these codings. Our experiments 3, 4, 5, you're going to build more complex circuits using Tinkercad. So experiment 3, you take a chip, U1, this is a 74HC08. Put it into your proto board. Hook pin 7 to ground, 14 to VCC, which is 5 volts, and then make the following connections, right? So here's a switch going from ground to 5 volts through a 1K. Feed that into input 1. Here's a switch going in input 2. Input 3 goes through a resistor and an LED and over to ground. Pin 6 goes to pin 7. That's a typo. There should not be a wire there. So don't connect pin 6 to 7. Don't connect pin 6 to 7. Alright, and then see what this circuit does. Make a truth table. So this is called input A up here. This is input B down here. So make yourself a truth table, A, B, and observe what the output does. And again, if your switch is open, that's a logic 1. If it's closed, it's a logic 0. If your LED is on, that's a logic 1. If it's off, it's a logic 0. So make a truth table for all combinations of A and B. Record what the output is. And then, once you've made this truth table, look at the data sheet for 74HC08 and make sure your truth table is correct. Alright, I recommend including a screenshot of your circuit diagram from Tinkercad, just to, demonstrate that you built the circuit. And then do the same thing down here with a 74HC32, with your inputs going to 4 and 5, your output from 6. And then one more time with a 74HC04 with your inputs on pin 1 and 3 and your output on pin 4. This one's a little more interesting than the other two. Takes a little more thought to understand the behavior of it. Alright, and then experiment 6. So the same three-way intersection. All the same things we said before. So west, south, east. Run the main west-east line horizontally. South goes to the bottom. East has highest priority. So right, it's still the same intersection as before. Still the same system diagram as before. And so okay, so sketch the intersection, draw the system diagram, generate the truth table. These should all be the same as what you've already done, unless your truth table wasn't correct or you didn't have a system diagram. But we've gone over what those should be, and so you should be able to construct a good truth table and system diagram. So the new piece on this is to draw a schematic diagram for your design using components available from Tinkercad. So this is going to mean coming up with equations. So come up with equations and then a circuit diagram. We'll talk a little about coming up with equations after the break, and we'll talk more about that on Thursday. And some people already did equations for Lab 1 for the last experiment. They made their truth table and then they wrote equations. So you've already done half of part 4, and now you just change your equations into a schematic. I think I got one schematic from someone too. So your schematic diagram should include a number of things. All right, components, wires, pin numbers, part numbers, switches, LEDs, etc. And we'll go through an example of that after break also. And then report requirements for each experiment. What are you trying to do? What's the procedure you follow? What did you observe? What did you conclude from it? And so on and so forth. And then for the entire lab, right? The cover sheet, lessons learned or conclusions, a new experiment of your own design. Cannot be a traffic light experiment. And then you need to actually perform the experiment and write it up as a new experiment. And that's lab 2, and that's due Friday. All right, so let's take a 5-minute break. We'll come back. I'll answer a question from Chad about translating circuits into breadboards. Then we'll talk about circuit diagrams, and then we'll go through the material you need to finish up the homework for Wednesday. So let's do a 5-minute break, and we'll come back at 9:28. All right, so see you in a few minutes. Wow. Oh man.
Yeah, I mean this is like the best snow I think we've had in years.
Yeah. Wow. Hopefully people's houses are covered. Yeah, if you take a walk, you need to stay out of the trees.
Yeah, I know, that's what I was telling her. So where she's playing, I told her she needed to stay over by her.
Yeah.
Yeah, you can hear them cracking
Yeah,
and falling everywhere. Like, yeah, like we need to go out in the middle of the street, I think.
Yeah.
You want some cocoa?
Cocoa.
Yes, with marshmallows.
Yeah, hopefully we keep power.
Oh, that's actually a good consideration.
Yeah.
Charge everything you got.
Yeah.
Yeah, that's smart.
What?
But don't say it out loud, of course.
Yeah. All right, welcome back.
What's it like to learn math on brilliant.org? Brilliant gives you hands-on to help you learn by doing.
All right, so somebody asked in chat, do you have a tip for translating a circuit diagram to a breadboard? I do, so let me post a video link in chat. And I'll send this to everyone. And I just tagged this onto the CSE 221 or 2021-22. But this is just it's a 10-minute video I put together a while ago that just kind of goes through taking a circuit diagram and figuring out how to place components in a proto board. And it's got kind of bad audio quality, sorry, but it goes through the basics and it might be kind of useful. So you're welcome to look at that if you like. And there's a link in YouTube, and it should be on the video list at some point today also. And there's a procedure you can follow for implementing circuits like that. All right, well, let me talk about the homework, and then if we don't get to how exactly to design a circuit diagram today, we'll do that on Wednesday. Let me make sure we get through the homework today because that's coming up. So homework 1, which you've hopefully done most of. So the first few questions are about converting between binary, decimal, octal, and hexadecimal, and we talked about those last week. But going from decimal into binary. So let's say you have a number like 137 and you want to convert it to binary. So you can do this with trial and error. You can know 128 is close to this, so put down a 1 for 128 and subtract, and you've got 9 left. So there's no 64s, 32s, 16s, there's an 8 and a 1. But there's a methodical way that we can do these conversions. And so I want to go through that in case you didn't see this in in 120. So here's what we do. We do 137 divided by 2, and what do we end up with? We get 68 with a remainder of 1. So, you know, divide this by a calculator. If it's odd, you'll get an integer, and there's 1 left over. And then do 68 divided by 2 equals 34 with a remainder of 0. 34 divided by 2 equals 17 with a remainder of 0. 17 divided by 2 equals 8 with a remainder of 1. 8 divided by 2 equals 4 with a remainder of 0. 4 divided by 2 equals 2 with a remainder of 0. 2 divided by 2 equals 1 with a remainder of 0. 1 divided by 2 equals 0 with a remainder of 1. And then 0 divided by 2 equals 0 with a remainder of 0. And we'll keep doing this. So in each of these steps, what I've done is I've taken this number and copied it down to the next line. I took the 34 and I copied it down to the next line. I took the 17 and copied it down, and so on. And then once I get down to 0 with a remainder of 0, this will just continue to be, you know, 0 divided by 2. And I'm still going to get 0 with a remainder of 0. So that goes on forever. Alright, once you've done this, these remainders give you your number in binary. So my binary number is going to be this. So 1 0 0 0 1 0 0 1. That's the binary equivalent for 137. And that always works. And that's a little easier than trial and error. And it's really easy to teach to a computer. It's a nice algorithm to code up. Alright, so what about negative numbers? With or without typos. Normally when we write a number in binary, like if we write the number 1001, we're thinking of this number as, you know, 1 times 2 to the 0 plus 0 times 2 to the 1 plus 0 times 2 squared plus 1 times 2 cubed, which is 1 plus 8, which is the number 9. And so the phrase I've used for this is weighted positional notation. Well, with weighted positional notation, the numbers we end up with are always 0 or bigger. Man, trees are just falling like something outside. If you're outside, stay away from trees. Because seriously, like, branches are coming down every few minutes out here. So what if you want to represent negative numbers? So we can use something slightly different from weighted positional notation, which is called 2's complement. And whenever we use 2's complement, we have to specify how many bits we're using. So suppose we're using 8-bit 2's complement. So if I wanted to write the number positive 9, it's going to be exactly the same as we just did. Right? 1 plus 8 is 9, and all these other bits are zeros. To get the negative version of a number, we're going to do 2 steps. First, we're going to complement each bit, and then we're going to add 1. So if this is my representation of the number 9, to get the number negative 9, I'm going to do 2 things. First, I'm going to complement each bit, 1 1 1 1 0 1 1 0. And then I'm going to add 1, 1 1 1 1 0 1 1 1. That's my 2's complement notation for negative 9. And I don't know if you did this in 120 or not. But it's a different way of representing integers that lets us represent negative integers as well as positive. So if you write your positive number in just plain old weighted positional notation and then you want to change it into a negative, complement all of the bits and then add 1 to that number, and what you end up with is the negative value of your original positive number. And so a few special values. And let's just stick with 8 bits. And it's always important that you know how many bits you're working with and that you use all of those bits. So suppose I want to find what -1 looks like. So I'm going to start off with the number +1, which just looks like this. But I'm going to list all 8 bits. So to find -1, what do? I complement all of my bits, so I get 1, 1, 1, 1, 1, 1, 1, 0. And I add 1. I get 8 ones. That's my binary representation for -1. This is binary. If I wrote it in hexadecimal, this would be a pair of F's. So when you're snooping around an operating system, when you're putting in Mac IDs or things like that, a lot of times you see numbers that have a whole bunch of F's in the beginning. Those are typically negative numbers. If you see something with 8 F's, that's a 32-bit 2's complement representation of -1. Alright, the number 127 looks like this. If I want to know what -127 looks like, complement each of your bits, add 1, that's -127. With 8 bits, the range of numbers I can express go from +127 down to -128. -128 actually looks like this. The number 0 looks like this. If I want to express -0, I would toggle all my bits. I would add 1. And I would end up with, again, 8 zeros. There's an extra carry coming out of the end here, but I just throw that away. So +0 and -0 are both the same binary representation, which makes sense because -0 is the same as 0. And this works for positive or negative numbers. So for example, consider the number 3. This is +3. If I want to negate that, I complement all the bits. I add 1. And I get this. This should be -3. If I want the negative version of this number, what do? Complement all the bits. Add 1. That's the negative version of -3. Well, -3 is just +3, which is what this is the binary representation for. So whether you're starting with a positive or a negative number, if you take its 2's complement, you get the negative of that number. And then the last thing to note is the most significant bit. If it's a 0, then it's positive, or 0. If it's a 1, your number is negative. So this most significant bit acts like a sign bit. It tells you if the number you're looking at is positive or negative. So there's a random 8-bit number. if I'm told that I'm working in 8-bit 2's complement and somebody gives me this number, what do I know? This is negative. And if I want to know what negative number this is, let's take its 2's complement and see what the positive value is. So if I toggle each of these bits, I get 0, 1, 1, 0, 0, 1, 0, 0. Add 1, 0, 1, 1, 0, 0, 1, 0, 1. This is 1 plus 4 plus 32 plus 64. That's 101 decimal, so this must be negative 101 decimal.
I have a question.
Sure.
So how is the structure of binary? Is it by force or like? So with let's say a 9-spaced binary number.
Okay.
The front one would be a 1. Would we count that as a 1, or would we put a 0 in order to make it in sections of 4?
So, let's see. I can think of a few ways to interpret that. So we're talking about 9-bit binary numbers?
Sure.
Is that what you were asking, or were you thinking about an 8-bit number?
I don't know how to phrase it.
So in general, when you're working with a computer or a circuit you're building or a question, right, you have to be told or you have to decide how many bits we're using to represent numbers. And that's just a decision that's made by, the designer of the circuit or the person who wrote a test question or something like that. But that's got to be specified somewhere. And so, for example, here I'm saying let's work with 8-bit 2's complement. So every number we write has a total of 8 bits. And if we wrote a number like this, typically we'll just say, let's just extend that to an 8-bit number by padding zeros. But we could, instead say, let's, pad this number with 1s. And so both of those are legitimate. And sometimes what we'll do is we'll say, let's see what this bit is, and let's use that to pad our number. So we would extend that into that. Whereas if we started with this number, we would say, oh, that's a 0, let's pad some zeros over here. And any of those might happen. There's different cases where any one particular of those might make the most sense. But usually if I give you a question, I'll try to be really clear on what it is I'm asking you to do. And if it's not clear, you should definitely ask for clarification, because it's probably something I forgot to specify.
Thank you.
You're welcome. All right, so 8 bits go from negative 128 to positive 127. 4 bits go from negative 8 to positive 7. And so we always kind of get one extra negative number because 0 kind of gets lumped in with the positives. So there's 8 numbers that could be non-negative and 8 numbers that could be negative. Because we know 4 bits you can specify 16 things. All we're doing is changing the representation of numbers with different bit patterns. With unsigned weighted positional notation, 4 bits would go from 0 to 15. Well, we're kind of shifting everything down. And we're saying, okay, so instead of 0 to 15, we're going from negative 8 to positive 7. So that's the deal with 2's complement. But with 2's complement, we can do arithmetic. And so, for example, suppose you wanted to do 12 minus 5. Well, 12 minus 5 is the same as 12 plus negative 5. And so let's do 6-bit 2's complement. And let's calculate what 12 minus 5 is. Well, the number 12 looks like this. It's a 1, 2, 4 plus 8. The number 5 looks like this. It's just 1 plus 4. So if I want to write negative 5, complement everything, add 1, that's negative 5. So I can write negative 5 equals 1, 1, 1, 0, 1, 1. And if I want to add these together, I do it the same way that I learned in school to do pencil and paper addition. I add column by column. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. Well, 2 is 1, 0. This is like adding 5 plus 5 in decimal. We get a 10, but we don't write a 10 down here. 1 plus 1 is a 2, but we don't write a 2 down here. We write that 0, and we generate a carry. And then 1 plus 0 plus 1, that's also 2, so we'll write down a 0 and we'll generate a carry. And 1 plus 0 plus 1 is another 2, so we'll write down a 0 and we'll generate a carry. And that last carry would generate, an outgoing carry of 1, but we just toss that. We're doing 6-bit arithmetic, so we're only going to worry about 6 bits. And so this is 12 minus 5 looks like this, and what is this in decimal? 1 plus 2 plus 4, it's 7. So we just found 12 minus 5 is equal to 7. And we didn't have to do any subtraction, we did addition, but we added a negative number. So the reason we do 2's complement to represent negative numbers is because it lets us just do plain old addition and still get the correct result. So question 6, unsigned or unsolved, wants you to do those operations. Take 123 plus negative 125. So do 8-bit 2's complement. Right, for each of these, do 8-bit 2's complement notation. Right, the 8-bit is critical. Radix complement is just another way of saying 2's complement. And so write down 123 as an 8-bit number. Write down 125 as an 8-bit number. Complement each bit and add 1 to write negative 125 as an 8-bit number. Add those together. And then take your result and convert that to decimal. How do you do that? Look at the sign bit. If the sign bit is a 1, you have a negative number. So take the 2's complement. And if you get 5, this is negative 5. If the sign bit is a 0, just write this down using weighted positional notation. That's the value you got. This is probably the question I'm going to grade on your homework. So do all the questions, but make sure you do this and make sure you do it very carefully. Write this in binary. Write this in binary. Do the pencil and paper addition of your binary numbers. Take the result. Thank you. Take the result, and if it's positive, that's your answer. If it's negative, take the 2's complement again to see what it's the negative of. So don't just say, this is equal to negative 2. Because we know that. We know 123 minus 125 is negative 2. But show that, right, by converting this to binary, adding them together, taking the binary you came up with, and if it's negative, convert it to a positive number and say this is 2, so that original binary I got was negative 2. Do that for all 4 of these. All right, and we did not get to question 9, so give question 9 a try, but I won't grade that one on your homework. So look at the notes in the book, do the best that you can, but we'll talk about this in class on Wednesday. But don't worry about if you can't get that one done, that won't be the question that I'm grading from your homework set. There's a good chance I'll grade question 6U. And you can see examples of how this is done in the solved versions, right? So 6 plus negative 3 is 6 minus 3. So here's what 6 looks like. Here's what 3 looks like. Here's the 2's complement of 3. And now 6 and minus 3 get added together. Here's the answer you come up with. That's positive 3. Alright, so you should be set on homework. We are out of time. That was fast, but thank you for coming on a snow day. Enjoy the afternoon. Come to lab hour or office hours tomorrow if you have questions about the lab or about the homework. We can talk about it in there. Otherwise, I will see everybody on Wednesday. Have a great one. Catch you next time. Thank you.
Awesome. Thank you so much. Have a great one.
All right. Thanks. You too.